All right, let's jump right in. Today we're going to talk about something that, kind of quietly runs our world in the background. It's scheduling in what are called distributed real-time embedded systems. Now, I know it sounds super technical and, well, it is, but it's the secret sauce that makes sure critical technology works not just correctly, but on time every single time.
I want you to think about this for a second. In a flight control system, or a medical device like a pacemaker, or even a self-driving car, being late isn't just a minor inconvenience. It's not an oops. It can be a full-blown catastrophe. So the million-dollar question is, how can we actually prove with stone-cold mathematical certainty that these systems will never be late?
And this isn't just some academic thought experiment, right? We're talking about real-world high-stakes stuff. These distributed real-time embedded systems, or DRE systems for short, they're the brains inside so much of our modern world. Think aerospace, avionics, critical medical tech. In these fields, sticking to a strict schedule isn't just a nice-to-have feature, it's the absolute bedrock of safety.
So what does real-time actually mean? A common mistake is thinking it just means super fast. But that's not the whole story, not even close. It's really all about predictability. For a real-time system, a correct answer depends on what it calculates and, just as importantly, when it delivers that calculation. A perfect answer that shows up even a millisecond too late is, for all intents and purposes, a wrong answer, period.
Okay, so how on earth do engineers build systems where being late is literally impossible? Well, it's not left to chance, and it's not just a bunch of testing, it's a rigorous science. Let's dig into the process they use to guarantee that on-time performance.
The secret sauce here is a process called temporal validation. And this isn't about just running a bunch of simulations and crossing your fingers. Nope, this is a formal mathematical proof. It's about demonstrating that a system will hit every single one of its deadlines under any circumstance you can possibly throw at it. We don't hope it's on time, we prove it.
And this whole proof thing, it actually breaks down into three pretty logical steps. First, you have to model the entire system. I mean, everything. Every task, every message, it all has to be mapped out. Then, and this is the really clever part, you calculate what's called the worst-case response time, or WCRT, for every single one of those things. That's the absolute, positively longest it could ever take. And finally, the moment of truth, you check that even that worst-case time is still shorter than the deadline. If it is, for everything, you've got a provably safe system.
Now, to find that worst-case time, you have to think like the biggest pessimist in the room. Engineers look for something called the critical instant. Just imagine the single most stressful moment possible for a task. It's when it needs to run at the exact same moment that every other, more important job in the system also decides to run. It's like a digital traffic jam. By analyzing that absolute peak load scenario, we can find the true upper limit and prove that even then, it's fast enough.
All right. So we know how to prove a system is on time. But what is the system actually doing? What kind of work does it have to get done? Well, to get that, we need to look at the workload, which usually falls into two big categories: time-driven tasks and event-driven tasks.
So you've got two main flavors of tasks. On one side, you have your cyclic tasks. Think of these as the steady, predictable drumbeat of the system, like a flight control loop that checks the airplane's wings, say 50 times every second. It's repetitive, it's predictable. Then on the flip side, you have sporadic tasks. These are the surprises. They're triggered by some external event, like a pilot pushing a button or a command zipping in from a ground station. The system has no idea when it's coming, but when it does, it has to react, and fast.
So now you have this interesting mix, right? You've got predictable, repetitive work happening alongside unpredictable, urgent events. This is where the scheduler comes in. The scheduler is basically the system's brain, and it has to decide from one moment to the next what's the most important thing to do right now.
And that brings us to a really crucial design question. When you have all these different tasks competing for processor time, how does a scheduler prioritize them all so that it can guarantee no deadline is ever missed? Not for the predictable stuff and not for the surprises.
Well, it turns out there are two main schools of thought on this. The first is called fixed priority preemptive, or FPP. The name kind of gives it away. The priorities are static, they're fixed. An engineer decides when they're designing the system, hey, task A is always more important than task B. It's simple, it's super predictable. The other approach is called earliest deadline first, or EDF. This one's more dynamic. The scheduler is constantly looking at all the tasks ready to go and gives top priority to whichever one has the nearest deadline. It's a lot more efficient, but also a lot more complex.
And when you put these two side by side, you really see the trade-offs. With fixed priority, FPP, you get that rock-solid predictability. It's way simpler to analyze and prove that it's safe. But the downside is you might not be using your CPU's power as efficiently as you could be. Now, on the other hand, earliest deadline first, or EDF, is a beast when it comes to efficiency. It squeezes every last drop of performance out of the hardware. But that dynamic power comes at a cost. It is much, much harder to analyze and prove correct. So at the end of the day, there's no single best answer. It's a classic engineering balancing act between predictable safety and raw efficiency.
So let's bring this all home. If you're going to remember just a few things from all this, what should they be?
Okay, 3 big takeaways. Number 1, real-time is all about predictability, not just raw speed. It's about guarantees. Number 2, for any system where safety is on the line, that mathematical proof we talked about, temporal validation, it's completely non-negotiable. It's everything. And number 3, choosing that scheduling algorithm, FPP versus EDF, is a core design trade-off. You're always balancing simple and safe versus efficient and complex.
And this all leaves us with a pretty fascinating question for the future, doesn't it? As we rely more and more on autonomous systems, our cars, our cities, our medical devices, all of those are becoming real-time systems. So the real question is, how will these fundamental principles of guaranteed, provable timeliness have to evolve to keep all of us safe in an increasingly automated world?
Hey, if you enjoyed nerding out about this with me, do me a favor and hit that like button, share it with a friend, and definitely subscribe so you don't miss the next one. Thanks for tuning in.